In a couple of recent videos, we've had a look at the Makin Compton organ setup that we've got at this museum's Not Obsolete. It involves a large tone wheel cabinet that has got a load of spinning discs and a bunch of relays and grids of contacts and things. It's a really interesting machine, and we've modified it to work with MIDI so it can be plugged in and played with all manner of stuff. And then in another video, we looked at the Compton organ console that we got, had a look in the back of it, seen all of the intricacies of these amazingly antiquated, very labour intensive, probably to build machines. And I've nearly finished banging together a circuit board to be able to midify that console as well. Alas, like everything, it is more complicated than I thought, but you just got to keep on cracking. So that video gonna be a couple of weeks still, but it's on the way. In the meantime, I wanted to touch on something interesting that I read about the actual electrostatic tone wheels. This is one of them right here. It's amazing on the inside, and in one of the previous videos, we actually played it with a drill, driving it with a belt, which is pretty funny. But in an interesting document that I found online about the history of making organs, it was written by Hugh Banton, who is actually of the Van de Graaff Generator band, but he was also an engineer in the Makin company and then a technical director in the Makin company. This document is really interesting. There is a link below on it, if hopefully I found it again. It outlines pretty well from the perspective of Hugh the history of Makin, and it touches also on the history of Compton organs. And it's very interesting. So the John Compton Organ Company was a pipe organ manufacturer founded in 1902. In about the 1930s, started experimenting with electronic organs, creating the melotone, which is initially creating the melotone, which is basically one of these but massive. It's basically, instead of having a load of small ones of these, one per note, it's actually got all of the notes in a sine wave on a disc. Initially built to only accompany a pipe organ. Later on, the electrostatic tone wheels were obviously developed to be smaller. This is actually quite a late one. That is one of the smaller types. It outlines the history and the development of Compton organ and how Hugh went on to develop a organ based on logic and discrete components. Very interesting reading, but the bit that interests me the most is the bit at the bottom in the, what am I talking? And there's a few like bullet points of like some quick tidbits about some things that weren't touched on. Talking about, for instance, in our quest to generate three-phase waveforms, we investigated a digital quadrature idea for quadrature modulation. But the one that interests me the most is this one. I'll read it out to you. By nature, Compton's rotary electrostatic generator is a very low capacitance device. One upshot of this is that despite the application of several hundred volts, that's right, in the one that we've got and all of them, it was about 400, 500 volt DC driving this. Where was I? Despite the application of several hundred volts to the stator rings, which is that stuff at the back, to receive a tiny audio output, just a few millivolts, and this level falls off alarmingly at lower frequencies. In an idle moment, one of us wondered what would happen if instead of DC, a low voltage radio frequency sine wave at say 150 kilohertz were to be applied and then rectified on the output side, effectively replicating an AM radio. That's right, classically, and in the Compton organ setup that we've got at the museum, this would receive about 400 volts DC or so on the back of this, and then as it's spinning, the audio output, which is on the output bits over here, would only be in the millivolt range. It's a big old loss, and for interactive stuff like the museum, imagine just having this. Having 400 volts sitting on the back of it just doesn't feel like a friendly idea. However, like what is said, instead of DC, a AC current of about 150 kilohertz, you get something back that is actually similar to the level that you put in. He carries on to say, it's a most impractical idea for organ building purposes, but it happens to work rather brilliantly. You get near 100% efficiency all the way down to very low frequencies. This is the bit that's funny. This experiment actually happened in the same month that I originally came up with the microchip system. That's the logic chip organ I was talking about. Mr. John was impressed and declared that if our electronic developments failed, we investigate this further, which gave us more incentive ... because it must have been a kind of dreadful idea to think of carrying on this stuff. But it's quite an interesting thing to hear that this actually runs at low frequency, provided you send an AC current in, or in other terms, a really high-pitched sine wave frequency. Now, I haven't tried this idea yet. I've been wanting to ever since I read that, but today is finally the day. Let's see what we can get. This being one of the sine wave ones, it's an opportunity to get back into this project because there's a lot of scope of messing around with this stuff. These electrostatic generators are really interesting. So basically, instead of the last video where we sent in high voltage DC, we're going to send in a really high sine wave frequency, well, a low radio wave frequency, something around 100 kilohertz. And we're just going to see what the heck the output sounds like. So it's going to be quite a simple experiment really. All we've got here is a speaker. So we've got a speaker here. So we've got function generator, and actually we can just listen to this. We can listen to the function generator by just plugging it straight into this. So here's 1,000. Oh, we can't adjust it if it's running. That's a bit rubbish. Let's go for what they said in the thing. So that's 150 kilohertz that. So if we press play, obviously you're not going to be able to hear that because it's way high, even beyond the dog's frequency of hearing. What we can do with this is basically see if it's going to affect it. So I'm going to plug a crocodile clip from the body of the jack, which is ground. Going to connect that to the body of this via this screw. Going to also connect the ground of the signal generator to another screw. So they're both connected to the ground of the electrostatic body, which I don't know whether that really matters, whether it's even connected, but now I'm going to connect the output of this. There's a bit of buzzing, but we'll sort that out later. That's not our problem now. Then we're going to get one of these, plug it into, I don't know, that one. I'm twisting it with the motor. You can see it's pulsating. That's the sine wave of it, just going backwards and forwards. It is there, going up an octave. It's doubling. It's just about how to get that. The 150 kilohertz. So speed that up. You can see there is a waveform there. We're starting to get the effect. Right, so it's a few hours later and I have cracked out the Science Fair 75-in-1 electric project kit. The reason why I've whacked this out is because we actually need a radio receiver to be able to make this work. Now I've done this, it actually makes a lot more sense about their findings. It's sort of like a spinning theremin. So the 150 kilohertz that they were talking about is a carrier frequency. So if you look at this, we may as well describe it with the actual manual. So this is crystal diode AM radio, amplitude modulation radio. Why is it amplitude modulation? Because if you look at this, this is what the radio looks like. It's got a really high pitched carrier frequency that goes up and down in amplitude like that. And we're actually listening, the voices on the radio and things is actually the amplitude of this. In order to receive the actual signal from this, you need to demodulate it somewhat. So you've got the antenna, and then you've got a variable capacitor, so you can actually change between the carrier frequencies that are the different radio stations. But for us, we actually just need one. And then we've got a diode that rectifies it. After smoothing it out and rectifying it, you don't get the carrier frequency anymore. You just get the amplitude, which ends up being its own waveform, which is your voice again. But in our instance, the amplitude modulation is actually the drawing on the inside of that electrostatic tone wheel that's over there. I don't know why I went for this. I could have used a breadboard, but I was fiddling around. This turned out easier, albeit it's a very noisy setup. I've been messing about. I've got the antenna coil still wired in. That goes over into this germanium diode. Why is it germanium? Because there's a lot less voltage drop than a silicone diode. And then that jumps over. So on a radio, it'll be a twisty knob, which is a variable capacitor. I've been messing around with this setup, and I found that this schematic works best with the tuning capacitor set to 4.7 nanofarads with a carrier signal wave. This is the radio station wave of, here's a signal generator I have, what is it, 120 kilohertz. So we've got 120 kilohertz radio station carrier frequency. This is just a test oscillator. We've got a carrier wave right here, actually just sending out a sine wave. I think it's plus or minus 5 volts. That's it. And that is sending out that carrier wave into the back of the electrostatic thingamajiggy. So the carrier wave goes into the back of the electrostatic tone wheel. Then at the front of the electrostatic tone wheel, that goes in to the radio receiver circuit, which is basically a demodulator that removes the carrier frequency and just gives us the kind of fluctuations that are created inside of here. So there's a lot of noise, but you can hear on the back. Get the high one in as well, see if we could get both of them. Oh yes! Yes! That's amazing. So now I've got that sort of working, I'm going to neaten up the circuitry and see if I can get rid of some of this background noise. That's awesome. Circuit is in very close proximity. It's all simplified. This is literally a resonant coil, a capacitor, and then a diode, and then an RC filter just to take out the top end. If I pull this off, you can hear. You can still hear the carrier frequency buzzing around near there. Now we've got a reasonably long wire. That's because in case we add some extra circuits here over to the output jack, which is right here. Just going to wind all of the wires together. A lot of background noise, but we'll get rid of that in a moment soon. Just gonna... Now I know that these all work together, I'm going to add volume knobs to them all, so they're voltage dividers, so you can adjust the levels, and then we'll worry about the output and get rid of that really nasty squidgy noise at the end. And then we'll focus on actually controlling the blooming thing. Nice bit of hot glue, never hurt nobody. It's all in a fun day of experimenting. You need your hot glue gun, that is for sure, if you're going to be doing this. So we're just going to get some wires, wire the output to one of the terminals of all of them, wire the ground to all of the terminals of one of them, and then wire a few of these into it, and we've got a mixer to mix the octaves. Ooh. So we're going to add a ground bus, which is basically just a bunch of wires. This basically means the potentiometer becomes a voltage divider, an adjustable voltage divider, also known as a volume knob. Ooh, lovely jubbly. I've only got a couple of spare ones of these, but it's enough to kind of develop on it, and then hopefully by the end of this whole experiment, I'll have built some very equivalent from cheap, modern to, you know, fine things. So we're going grey. That seems to be the next one, or is it? Yeah, grey and then green. We're gonna go down the octaves. Arduino to be able to drive a motor. This is just a random motor I've got in the bits box. I think I used this in the Leslie speaker. Oh, my table's got all messy. I hate it. Nothing worse than a messy table when trying to do this stuff. It's just everywhere. It's a blooming jumble. Hot glue goes a long way. Look at this. The great thing about hot glue is it's not amazing, and with a tiny bit of WD-40 or something, you can just pull it all off again. So very handy for prototyping. Literally going to burst power it through the voltage input, which is basically this on the Arduino board. It might cause the Arduino to crash. If that's the case, we'll we'll move it around and stuff. And then we get a 12-volt power supply, plug that in like that. Now, that's powered on, that's powered on. Cool, cool, cool. Oh, and then, oh my son, it's in the screw, it's in the drill wonky. Right, so we got this. We got this. We're just gonna cable tie it. Okay, just plunk this on here. Pull that up. Come on. Yeah, baby. This setup obviously isn't ideal. This is made for like toy RC cars and all that stuff. So, you know, when I get this sorted, I'll use a H-bridge or something. But right now, let's just see what we could get out of a solid tone. Right, put this on here. Or you could be like me and fry your Arduino like a blooming idiot. Okay, right, where was I? Let's get up a bit of speed. Quite subby, right? So this is the lowest note. So the lowest note, the next lowest note, the next lowest note. In the next video, I'm going to be focusing on a circuit that is more in keeping with this kind of circuit inside here. So as you can tell, there is a long way to go, but this is me bashing things together of what I had in bits boxes here and there. So what do we need to do? Well, we need to improve basically every single aspect of it. We need to make a oscillator that replaces the function generator, an oscillator circuit. It also means we could probably send a larger voltage carrier signal in here, because I think this one only does 5 volts, but if we're going to be running on a 12-volt power supply, could probably do 12 volts into here, improving the signal to noise ratio. Then we're going to have to make a better receiver circuit, which is going after it. I'm going to push the frequency back up to about 150 kilohertz, so it works with some little bit more off-the-shelf components for the radio receiver circuit, which I think in turn will reduce the noise floor. The simple volume control to be able to control the fundamentals and the octaves that are in the actual tone wheel themselves is really simple and nice, and it proves that it can work even with the simplest of setups. And obviously we need to improve the motor drive circuit. Ultimately we're going to go for something a little bit more in keeping with what's going on inside of here. Make it also voltage controlled, which means we'll be able to control which notes it's playing, and potentially by then be able to control it quite quickly, much like this, but more in tune. So yes, it's drive circuit, it's carrier frequency circuit, and the radio demodulator circuit. That's basically what we've got to do to improve this setup. I did put up a short of this the other day, and people were mentioning about this being all well and good, but a lot of crosstalk might happen if you convert a whole organ into this. This is true, I'm not converting the whole organ. That would be a heinous crime to modify that organ, we're keeping it as it is. And also, hypothetically, I don't think it will be as much of an issue as you'd think. Yes, outside radio interference might mean that it would need to be in a big metal Faraday cage or something, but hypothetically, inside of it, the crosstalk would be minimal because you're sending the same carrier frequency into all of the relays. Then the relays go into this and get modulated. And then all of the outputs of these literally get mixed together because they have the same carrier frequencies and then get demodulated all together afterwards, working much the same as the Compton works now. Crosstalk is very likely not at all an issue. Anyway, with this and midifying the Compton console, I've got a lot of work to do. I'll be updating it all over on Patreon as and when I finish it. For instance, this stuff has all been on Patreon way before it. And likewise, if you want to download sample instruments and samples and extra videos and stuff, it's over there, which is a humongous contributor to being able to make these videos and this project possible. So thank you very much for the support on there. And anyway, until next time, I'm Look Mum No Computer. This is the electrostatic Compton organ tone wheel. And remember,